today we're going to start reaction stoichiometry. This is finally all the stuff we've been working towards this whole semester. We all put it together now. And so it's just dimensional analysis. This time we're going to use balanced chemical equations to figure out our dimensional analysis, but it's very similar to what we've been doing. We're just going to put it all together in a neat little package now. Okay, so we're going to talk about what the coefficients mean in balanced equations. We're going to use balanced equations, and we're going to go use the moles of product and grams of product. So we're going to go to moles, we're going to go to mass, and then we're going to figure out this really cool fun thing called limiting reactants, which reactant gets used up first. And then we're going to compare the amount of product we actually obtain to the amount we think we should obtain, right? And so we're actually going to be doing a lot of this in lab, not next week, but the week after. We're actually going to be doing a very similar problems to what you're going to see in lecture right now. Okay, so talk about balanced equations, then we're going to do mole-mole conversions, mass-mass conversions, and that's about all we're going to get to today. But again, this is so similar to what you've already done. So let's just review our balanced chemical equations, right? Oh, hey, just a quick review. What kind of reaction is that if you had to classify it? Who remembers? What kind of reaction?
Single displacement.
Yeah, it's a combustion reaction. Yes, right? It was a couple chapters ago, right? Single displacement looks kind of like it, yep, but how do we know it's a combustion reaction?
Water and CO2.
Yeah, that's the key. That water and CO2, that's the key to the combustion reaction. By the way, I'm not going to make you classify these reactions, okay? But you will have to figure out the products. So hopefully everybody has those notes because we're going to be talking about those again. Okay, so now let's look at this combustion reaction here. By the way, this is propane. This is like what happens when you grill. So here's our grilling equation, right? Here's our propane. The coefficients, again, this is understood to be a 1. This means we have 1 molecule of propane, 5 molecules of oxygen, 3 molecules of carbon dioxide, and 4 molecules of hydrogen, right? And so, again, 1 molecule, remember this is a 1 here, even though it says it 5, 3, and 4. But we can also say that this is 1 mole, right? Remember we talked about how like 1 molecule, if I said, hey, could you give me a molecule of propane? And you'd be like, no, because how would you get a molecule of propane, right? It's too small. That's why we deal in moles. Moles make everything big enough so we can actually use them, right? So that means that 1 mole of propane, 5 moles of oxygen, 3 moles of CO2, 4 moles of water. This is what stoichiometry is going to deal with. So we're going to talk about those coefficients and how we use those. So stoichiometry just deals with the calculations about the masses of reactants and products involved in a chemical equation. And so what we're going to do is we're going to have a certain amount of our reactants, and then we're going to use unit conversion like we have been doing, and we're going to figure out how much products we have, and we'll even be able to calculate how much is left over. So when we do this, we need a balanced equation. Oh, so we are going to be balancing equations. Okay, so Nathan, I'll go back at the end and help you with that. Okay, so we're going to use food. And I know this is hopefully how people eat before lecture, just because, yeah, because I'm always going to use food to do this. Okay, so let's say we're going to make a sandwich. We're going to make a cheese sandwich, and we're going to make cheese sandwich very frugally. You get 1 slice of cheese for 2 slices of bread. That's it. So if we want to make as many cheese sandwiches as possible for lunch, if we have 20 slices of bread, how many slices of cheese do we need? Right? We already, right? If we have 20 slices of bread, 2 slices of bread for every piece of cheese, no extra cheese. Gilbert. We need 10 slices of cheese, right? That, what you're doing in your head, that is stoichiometry. So you've been doing this for a long time. So here's our balanced chemical equation. 2 bread slices plus 1 cheese slice. This gives us 1 very basic cheese sandwich. Now, if we do that using our math, if we start with 20 slices of bread, and then we use the relationship because we have 20 slices of bread. We have 20 bread, but we want cheese. We need to use the relationship between bread and cheese. And so we can see that there's 2 breads for every 1 cheese, which gives us 10 cheese slices. Right? And again, you like it with the parentheses or whatever, that's fine, just 2 different ways to write this. So this is very similar to what we've done before. Just this time, the relationships are coming from these coefficients in the balanced chemical equation. Okay, let's try this with a reaction now. So we have carbon monoxide reacts with oxygen to make carbon dioxide. Here's my question. How many, you guys are funny. How many CO2 molecules are produced from 2 CO molecules? So if we have 2 CO molecules, how many CO2 molecules do we make? So try this. The first couple might be a little difficult, and then you're going to get really good at this. So that's my question. How many CO2 molecules are produced from 2 CO molecules? So if I have 2 of these, how many of these do I make? Yeah, do you see how we're literally just looking at that coefficient? Let's try another one. This one should be easier. Now that you know how to do this, how many O2 molecules are needed to produce 2 CO molecules, CO2 molecules? Well, I just gave you the answer. Yeah, 1. All right, this one I'm not going to give you the answer to. Try this one now. How many CO molecules are needed to react with 1 O2? I'm going to wait for a few of you now this time. And you can just put the number down if you want. Yeah, so you can see if we have 1 O2 molecule, 1 O2 molecule is 2 CO molecules, right? So we're just looking at the relationship between these 2 things. Now, if we use moles, which you're going to see some great mole pictures now, how many moles of CO2 are produced from 2 moles of CO? So if we have, how many moles of CO2 are produced from 2 moles of CO? Yeah, we do the exact same thing because now we're just talking about a mole, right? Now we're making to a quantity we can actually measure and actually work with in our lab. Okay. How many moles of O2 are needed to produce 2 moles of CO2? How many moles of O2 do we need? Yeah, 1, right? I know this gets, the more we get into this, the easier this will become. All we're doing is we're looking at the numbers in the balanced chemical equation. Okay, last one. How many moles of CO are needed to react with 1 mole of O2?
2.
Yes, so this is becoming, right, much easier. What we're doing is we're just looking at those coefficients. Now, look at that mole. It's not as cute as the others. Okay, so if we do this now I'm going to show you how to do it with, sometimes you can still, by the way, some of you are still going to be able to do this just by looking at it, but I'm going to show you how to do this using our unit conversions that we've been doing. So if we have 6 moles of CO, and we want to know how many moles of CO2 will be made if we use all of the CO. So in this case, we have 6 moles of CO. And we want moles of CO2. And so if we're going to do this using stoichiometry or unit conversions, very similar to what we've been doing, we're going to start with moles of CO, and we want CO2. So we're starting with CO and we want CO2. So we need to find the relationship between CO and CO2. And again, the moles of CO will go on the bottom because we need to cross off our units. And we get these relationships from looking at our balanced chemical equation. So we look up here to figure it out. So if we look at CO, there's a 2, and we look at CO2, there's a 2. And we cross off our units, and we get 6 moles of CO. And again, however you like writing it is fine with me. Okay, so now, this time, I'm going to have you try this one. Okay, so try this one. And again, if you don't want to type it in the chat, that's fine. You can do it. You can send it privately. You can text it to me if you don't want to put it in the chat, or just write it on your paper and see if we get the same answer. So try this one, and let's see if we can get this. So I'll give you a minute. Abby, the answer to the last one was 6. All right, so I'm seeing a lot of these. Very nice. Okay, so now, if we look at what we have, again, I'm giving you the answer. I'm going to change my color. Yellow, so much prettier. Well, I guess I'm not changing my color. So if we have 6 moles of CO, I'll worry about my sig figs later, and they want how many moles of O2, this is what we're looking for. We want moles of O2. So this means we need to figure out the relationship between CO and O2. So because moles of CO is what we're starting with, that's what's going to go on the bottom. And the relationship between them is going to come from the coefficients in the balanced chemical reaction, right? And so now we need to decide, we want CO and O2. So 2 COs to 1 O2, and we end up with 3. And again, when we do this, just remember our sig figs, right? 2 sig figs, 2 sig figs, right? And remember, so if this was on your quiz or your exam, right, plus 2 points for the conversion. Now, remember why I was telling you last week that it is so important that you not only write the mole, but you also write the label? This is why, because now we're going to different pieces in the reaction itself, and you're going to get lost. I know it's like, I don't want to write that much. I get that. But it is so important that you not only write moles, but you also moles of what? If we were in class, if I saw you write it, I'd be like, moles of what? And I'd be like, unicorns, rhinoceroses, pencils, ice cream. And I would keep saying random words until you said CO, moles of CO. But I can't be over you doing that right now. Okay, so this with the label and the unit, right? Plus 2, plus 1 for your answer. Plus 1 for your sig figs, and plus 1 for your unit, right? So you need to have all of these pieces while you're doing it. Trust me, it's going to save you hours of agony if you do this versus not doing this, because you're going to get lost later on. Okay, this is a star mole. Isn't it cute? It's such an ugly mole. Okay, let's try this one. How many moles of CO are needed to produce 7.5 moles of CO2? Okay, so I want you to try this one all on your own. It's totally fine if you get this wrong. We're just starting it, right? I know tons of you are sending to me privately with question marks. That's perfect. This is the foundation of kind of the rest of the class, and like 60% of 70% of Chem 219, which is the next semester. So we really want to try these now so we can get this concept down, and then we'll be set. So try this now. I'm going to give you a minute and then type your answer in the chat, and then we'll go over it. I'm seeing a bunch come through. I'm going to give you guys another minute. Yes. Very good. Okay. So if you're having trouble with this little have and want, it's going to help you direct and focus on where you're trying to go to in what you have. So if we start with 7.5 moles, and this says how many moles of CO. Oops, I just wrote want again. Moles of CO. Yes, I'm seeing lots of them now. So again, if you're like, I don't know where to start, I don't know what to do, start with the number they give you. 7.50 moles of CO2, right? And now let's say, I don't know what to do. I don't know what to do. Whatever unit you have here, put it on the bottom. At least you can do that, right? That's the least we can do. Now, if we look at what we want moles of CO. So now we think, if we want moles of CO, is there a relationship between CO2 and CO? CO2 and CO. There is. There's 2 CO2s to 2 COs, and then our units cross off, and we end up with 7.50 moles of CO, right? Okay, so let's do that all neater. These are cracking me up in the chat. Don't worry, we have lots of food examples coming up when we do limiting reactants. Okay, so we get 7.50 moles of CO. Okay, now let's try one that's got a little more oomph to it. Okay, so the rebreather units used by firefighters convert exhaled CO2 to oxygen gas. Here is, and I'm giving you this balanced chemical equation, but can you see what's going to be happening later where I only give you, just like we did in our reactant section? Remember what, our chemical reactions, when I only gave you this and you had to like predict all of this? Yeah, that's going to come up. Not today though. We won't do that today. Okay, so this problem's got a little more to it. So it says how many grams of oxygen can be produced from 1.4 grams of potassium superoxide? So in this case, we have grams, 1.40 grams of KO2, and we want grams of oxygen. So when we're doing this, this is your map, right? Use this balanced chemical equation. Now, how do I know that I need this chemical equation? It's asking for grams of O2 and telling me we have KO2. So they're asking for something else. When you have something, but they're asking for something else, in the middle, you have to do a mole-mole ratio, which is the mole over mole. So that means that I need a balanced chemical equation. So that's how you know that you need that balanced equation, because they're giving you KO2, but asking for O2. So somehow we need to figure out the relationship between KO2 and O2. And that relationship is there are 4 KO2s to 3 O2s. Right? And so that's how you know we need a balanced chemical equation. So if our relationship is 4 moles of KO2, I'm going to do it like this, to 3 moles of O2. I can write that like this, 4 moles of KO2 over 3 moles of O2, or 3 moles of O2 over 4 moles of KO2, right? All of those are the exact same thing. And I got all of them from looking at this balanced chemical equation. Well, you can see in every single one of these ways that I'm writing this, we need to have moles, but we're starting with grams of KO2. Can we go from grams of KO2 to moles of KO2? How do we do that? If we have grams and we want to get to moles, where do we look?
Molar mass.
Molar mass, which we get from
The periodic table.
Periodic table, right? So whenever you know that you need to get to moles and you have grams, periodic table should go right in our brain, right? So if we start with grams of KO2, I have to erase all my nice handwriting here. Then we can convert to moles, right, using the periodic table. And because you all are so good at molar masses now, I'm probably just going to give these molar masses to you now, because adding them up, you're really good at that. Then after we get to moles of KO2, then we can convert it to moles of O2 using the relationship. And again, the relationship are just these coefficients in front of the balanced chemical equation. Now, once we're at moles of O2, we want grams of O2. So if we have moles and we need to go to grams, where are we going to look again? Yes, periodic table. And important here, very common mistake people make, this is O2. So when we do the molar mass, it needs to be 16 times 2, right? So careful with that. Yeah, it has to be 32, not 16, because there's 2 of them. Okay, so we're going to try this. So I'm going to do one, and you're going to do the next one. So here's our little kind of outline that we're going to use. And so if we start with 1.40 grams, and again, I'm going to write the have and the want here, just to show you why in a second. 1.4 grams KO2, we want grams of O2. So if we start with grams of KO2, we need to get rid of this. Pretty sure the molar mass was 71.1, right? Grams of KO2 to 1 mole of KO2. Okay, by the way, if you can do this faster than I can, go ahead, do that and type it in the chat. Now, if we look at our units, the reason, again, I just went to moles is because I have KO2, but I want O2, right? So I have this, but I want this. The only way I can convert that is to go to a mole-mole ratio, which means I have to get to moles first. Now that we're at moles, now we can use this mole-mole ratio. I'm going to do this in a different color for a very specific reason. Now, again, let's say I don't know what to do here. I'm totally lost. This unit is on the top. I'm not going to use blue. Hold on. I'm going to use white. White. There we are. So moles of KO2 goes on the bottom. And here's why this little want thing is nice. Where are we going? We're going to O2. It kind of keeps us on target of where we want to go. And then the relationship between these two, these numbers, are going to come from the balanced chemical equation. Now, we cross off our units. in this case, we are now at moles of O2, but we did not want moles of O2, we want grams of O2. Again, that's where this have and the want kind of keep us on track and focused of where we want to go. So we don't want moles. So that means moles of O2 have to go on the bottom, right? If moles of O2 has to go on the bottom and we want to go to grams, moles to grams, periodic table, right? And 1 mole of O2, again, is 32 grams of O2, not 16, because this is O2, right? And then if we look at our units, moles, we are left with grams. Grams is exactly what we wanted. And I can see so many of us already have this answer in here. Now, how many sig figs can I have in my answer?
3.
Yeah, because this is 3 sig figs. So that means we have to have 3 significant figures in our answer, right? The last thing we do every single time is check these sig figs. And so I think it's 4, 7, 3. That looks like the consensus. I'll do it again in a second. Grams of O2. 0.473. Okay, now I want you to notice something here. There's a reason why I did this one in the middle in a different color. This is the only new piece, right? This we did last, right? We did that last chapter. This we did last chapter. This is the only new thing. This is it. In this entire module, this is it. All we're going to be introducing is this new concept of going from one piece of our chemical equation to another piece of our chemical equation. But you already know how to do the rest of this. So this is our new piece that we're going to be introducing. Okay, so now I'm going to show you all of this meter. So again, use our molar mass, cross off our units. At this point, the reason we went to moles here is because we wanted to do a mole ratio, right? We call this a mole ratio or a mole-mole ratio. And we have KO2 and we wanted to get to O2. So we use the coefficients from our balanced chemical equation, cross off our units. We wanted to go to grams. And so there we are, grams. Okay, and again, 3 sig figs because we started with 3 sig figs. So now, again, this is it. This is all new. This piece is the only new piece. All of this, you've probably done 50 times by now, right? So it's just this one new little piece, and these numbers, again, this is why this KO2 here that you write the moles and you write the KO2, that's how you know that the KO2 goes on the bottom. So you have to write the mole and the KO2 here. You can't just write mole, because if you put mole here, well, then moles of what is this, right? If you don't put the units here, let me show you how weird that looks. How do you know what goes where, right? How do you know the 3 versus the 4, right? You don't know where to put it unless you can actually see the units, right? So you need to make sure you write what you're talking about after it. That's what's going to help you keep you on the right track to the end. Look what happens. I'm going to just take all these out. This is what I see sometimes from people. How do you know that's right? Right? How do you know you ended up with grams of KO2? There's no way of following your work right now, right? It's just sheer luck that you put the 3 on the top and the 4 on the bottom, right? And a lot of times when students mix it up, it's because they didn't put these labels. These labels are the key to these questions. Okay, ready for your own? I want to remember these molar masses. 71.1 is KO2. All right, try this one. KO2 is 71.1 grams. It's okay if your work, okay, so I think we all agree that I have pretty bad handwriting, but you can have bad handwriting, you just gotta be organized. That's the key, it has to be organized. It doesn't have to be neat, just needs to be organized. Okay. Leave yourself extra room while you're doing these as best as you can. Leave yourself extra room. I tried to, on your lecture notes, give you a whole box for this. Okay, so try this one and then see what you get. And by the way, if you get this, you're gonna be like set into like 219 and for the rest of this class, because this is kind of the basis for what we're doing for the rest. So take your time and really focus on these questions. All right, I'm gonna give you a minute. Type your answers in the chat, and then we're gonna go over it in just a second. All right, I'm seeing a bunch of them now. And again, if you get these wrong now, it doesn't matter, right? Our goal is to figure out what part we get stuck on right now, and then we'll work through it so by the time we get to our quiz and our exam, we're all set. But we want to work through it now in lecture and not work through it in our quiz and our exam, right? So it's okay if you're not getting them right now. This is the time to work them out and work out all of our little kinks we've got. Okay, are we ready? Is everyone ready, or do we need another minute? Good, yes? Okay, so when we start this one, I gave you this molar mass. Right now, again, let's say that you're like, I don't know where to go from here. You know what we do know? Grams of KO2 has to go on the bottom. And when we look at this, what do we have? We have 1.40 grams of KO2, and we want how many grams of CO2? So we have this, but we want to go, oops, here to CO2, right? So somehow we need to, they're giving us something, but asking for something else. They're giving us KO2, but asking for CO2. In that case, that's how we know we need to do that mole ratio, the mole on top of mole. The only way to do that is to get to moles, right? So if we have grams right here, we have to think, oh gosh, I need to get to moles. And so we look at the periodic table, and remember the units of the periodic table. So if we have KO2, it's 71.1 grams of KO2 over 1 mole of KO2. That are the units of the periodic table. Every time you look at the periodic table, the number you are seeing, the units are always grams of whatever you're reading over 1 mole of whatever you're looking at. Those are the units of the periodic table. So 71.1 grams over 1 mole of KO2. And when we do this, cross off our units. Now again, if we're like, I don't know what to do next. Well, we know we don't want mole of KO2. We need to get to CO2 somehow. That means that moles of KO2 must go on the bottom, right? If moles of KO2 goes on the bottom, now we're at moles. So if we get moles of KO2, moles of CO2, we can figure that out, right? We want to go 2 moles of CO2. We look at our coefficient, or 2. Oops. Cross off our units. And now we're at moles of CO2. We're almost done. We want grams of CO2. So if we want grams of CO2, we know when we look at the periodic table that 1 mole of CO2, something like
44.01.
44.01, thank you. 44.01 grams of CO2. Thank you. Okay, cross off our units. And when we do this, we get 0.433 grams of CO2, right? And again, 3 sig figs, because we started with 3 sig figs. Yes, so again, the whole point of this is we were trying to get to this new piece, this mole-mole ratio, right? When you have something and you want something else, you've got to do a mole-mole ratio in between. So we have KO2, but they're asking for CO2. That's how we know we need a balanced chemical equation. That's literally the key. They're like, whoa, those are 2 different molecules. Yes, that's why we need a chemical equation. That's where this balanced chemical equation comes in, is when you see you have something, but they're asking for something else. In the middle, somehow, the only way you can convert from one thing to another is using this mole ratio. Okay, so let's look all of that neater. So here it is, way prettier. So much prettier now. See, this is when we look at the relationship from one to the other. That's the whole goal of this problem. We get those numbers from the balanced chemical equation. Cross off our units. Now we can go to grams. And we get 0.433 grams of CO2. Okay, any questions on this one before we try another? All good? Yes? Okay. Well, here you go. I'm not going to help you at all now. There's no help out on this one at all. I'm giving you the balanced chemical equation. You're welcome. But I'm not going to tell you what you want or where we're going or how to do this. Okay, so try this one. And then let's see how we do on this. Again, you can either send me it via Remind on your phone or type it in the chat. And if you don't want to do it publicly, just type it privately. It's fine. Either of those are always okay. You guys are going fast on this. And it's okay if you're not going fast on this right now. If this comes naturally to you, that's awesome. You can help your other classmates, right? Those of you who are jamming fast on this, I'm going to give everybody else a little bit more time. You can try this next one too. Oh yeah, you guys are looking for the molar masses. KO2 71.1. And CO2 is 44.01. I'm going to give you a little bit more time. And then again, those of you speed demons, do the one on the bottom. I'm seeing a bunch of them come through now. Yes. Very good. Okay, we have about half. So I'm going to write this. I'm going to go slowly. And again, those of you who have already, you can work on that second one. I know a lot of you guys are going quick through this, which is fine. And if you're not going quick through this, that's okay. We just started. So if we start with our grams of O2, then we're going to start at O2, and this time we're going to go to KO2. So we're going to need to figure out the relationship from O2 to KO2. So that means we have to do, I'm going to erase our molar masses. So if we have moles of O2, that means this is our time to go to KO2, and then we go to grams of KO2. I put that too high. Okay, so I'm going to write this. While you guys are finishing this, I'm going to write this on here. So that's supposed to be a 0. Okay, so if we start with O2, again, since grams of O2 is here, grams of O2 has to go on the bottom. And our whole goal is to go from O2 to KO2. The only way we can go from something to something else is a mole-mole ratio. So we have to convert our grams to moles. And we know from our last module, grams to mole, periodic table. And again, the most common mistake once people get good at this is this right here. It's not 16. There's 2 O's, it's 32. And a lot of you that get this really fast, these are the simple mistakes you make, so be careful on those. Okay, now we can do the mole-mole ratio, right? And this again is coming from our balanced chemical equation. We're not stopping at moles because they asked for grams of KO2. So we're going to go to grams of KO2 again, using the periodic table again. And we get 16.9 grams. Yes. Okay. Now, how about, okay, are there any questions on this one, first of all? Anything? Feel like we're good on this one? Okay, good. I'm going to let you write that one down. And then I want you to look at this one here. I know, see, look at everyone who says that you have horrible handwriting and it looks like a jumbled mess. Look at my handwriting. It's not pretty either. It's okay. Okay, so our next one, how many moles of O2 are produced from 5.7 grams of CO2? Now, what is different about this problem than the ones we've been doing? There's one little difference. What is it?
We stop at moles instead of grams.
Yes, that is the key. So remember how I keep writing like, oh, I have, I want, I have, I want? There's a reason why I keep writing that. The reason is especially once you get really, really quick at writing, at doing these, and we've gone through this a few times, there's so many times that people give me the right answer or the right answer to the wrong question. Like, for example, in this case, we have 5.70 grams of CO2 and we want moles of O2, but we get kind of fast at doing this, right? So we're like, okay, 5.70 grams of CO2, and you're like, I'm so good at this now. And you're like, in 1 mole of CO2. And then you're like, oh, this is a time for the mole ratio. CO2 to O2. 2 moles of CO2 to 1 mole of O2. And then you're like, oh, I really get this. I know exactly what I'm doing. And then I get this answer, right? And the answer that half the people will give me is this. I know you're not going to do it, but this is what happens a lot. I get 2.07 grams of O2. And then I'm like, oh man, and then they get it wrong. What's wrong with this answer?
They gave you grams when you wanted moles.
Yeah, we were done right here. We were done. The problem was done. This was not needed, right? A lot of times when we get really good at this, we go so fast that we give the right answer to a question that was not asked. If I had asked grams of oxygen, that would have been right. I didn't ask that, right? The question asked for moles of oxygen, right? We were done right here. We did not need to go any further. So 0.194 moles of O2, right? So this is why this little have and want kind of helps a lot, because in the end you go, oh, moles of O2. Oh, yep, that's the unit of my mom. That's the unit I want. Right, we're good. So careful, like very, very, very careful of that, right? Make sure the unit you end with is the unit you're actually supposed to give. Okay, so now we're going to do a really fun question. And this is going to test how well we do this. Okay, so this is just a combustion reaction. And hey, does anybody remember when we did this in lab? Do you remember the lab when you had to do the splint test and it popped and it scared you?
Yeah.
This is that. Yeah, everybody's like, yeah, I didn't like that. Right? This is the exact reaction. Okay, but now we're going to use this in the shuttle launch. So in the shuttle launch, 1.8 times 10 to the 8th grams of hydrogen is used in the liftoff during a shuttle. I want to know the mass of oxygen that's consumed. I want to know the mass of water vapor is produced. And then I want to know, does the mass of the water vapor equal the mass of each reactant? And if it does, what law describes this observation? So this is a 3-part question. Okay, so the first part, we want the mass of oxygen gas. Second part, we want the mass of water. So we have 2 questions here. And then the next part is we want to know if the water vapor equals the mass of both of our reactants. Okay, so let me see here. I'm going to break this up for you into first question first. Okay, so I want you to try this one. It's okay if you don't get it correct right now. We're just going to try it and see how far we can get on this. And again, if you can fly through all these, just start typing them in the chat and we'll go. And I see a few of you already finished it. Nice. Okay, so grams of oxygen first. Let's go there first. And again, if you're going faster, go straight to your grams of water and then see what we can get in our end. And if you have any questions while you're going through this or you get stuck, just feel free to send me a text or type it in the chat. And you have all of these on your notes. So if I turn off the screen for a second, you can keep going. This is a great practice for your calculator too. right, I'm seeing a bunch come through. Want to make sure everyone puts this in your calculator too, because this is a good one with the calculator. By the way, this is H2, right? So it's going to be 2.016 grams of hydrogen, not 1.008. Yes, I'm seeing a lot. Okay, I'm going to write this on here. And then I want to make sure everyone puts this in your calculator because I'm seeing about 7 different answers, which is okay. That's totally fine. 2 moles of hydrogen, again, coefficients. I'm going to oxygen, 1 mole of oxygen. Again, it's O2, so it's 32 grams of oxygen in 1 mole of oxygen. Okay.
All the way around.
Over.
Very nice. Right? What was wrong with, oh, should have left it there, right? 1 mole of oxygen in 32 grams of oxygen, right? Because we have to cross off our units. 32 gram goes on the top. Again, follow our units and then we put it in our calculator. Maybe. I'm seeing a bunch of different numbers. Put this in your calculator. Is there anything wrong with what's written right now? We fixed my mistake that I made, yes? Yes, we're good? In your calculators, you should have the entire top divided by the entire bottom. Again, we've worked with your calculators a bit now, and all of your calculators work a little bit differently. So the whole top divided by the whole bottom. Now, some of your calculators don't need to do this, but those of us know which calculators need this, right? Those of you with the gray and white one, lots of parentheses. Lots and lots of parentheses needed. I'm seeing, okay. So I got 1.43 times 10 to the 9th grams of O2. And again, yes, 2 sig figs, I agree. But everyone put this in your calculator. I want to make sure, because there's so many different answers right now. I want to make sure that everybody gets this question. Or then you actually get this answer.
Oh, I see what I did wrong. I accidentally, because I wasn't looking at your work, I accidentally did 2 moles of O2 because I thought O2 would be 2 for some reason.
Oh yeah, that's actually really common, right? So this box right here, these numbers can only come from in front of this doesn't matter what molecules they are, the numbers can only come from in front of the molecule that you're talking about, right?
Right.
And then I'm seeing a bunch of numbers. Yeah, okay, so let me see. Here's what my calculator says. My calculator says 1.42857114. You don't need any more numbers than that, times 10 to the 9th. So again, those of you that are not getting this number, put this in, hit enter. And then hit divided by, open parentheses, 2.016 times 2 close parentheses. Then you should get the right number. What happens if you don't use these parentheses on the bottom, depending on your calculator, is your calculator will take 32 and divide just 32 by 2.016 times 2, and you're going to get a crazy number. Now, again, not all of your calculators need that, but we've worked on these so much, I'm hoping that everybody's good with these. All right, I'm seeing lots of the same number now. Okay, and again, sig figs 2. Okay, 1.4 times 10 to the 9th. We're all going to remember that, yes? Let's try the next one. Massive water vapor now. So we're going to do the same thing. This time we're going to go to water. And we have to remember our first number, 1.4 times 10 to the 9th.
Professor, the last one, when I put it in my calculator, I don't get like the times 10th to the exponent number. I only got like a super long number, like 1.42857, and then going further.
Can you text me a picture of your calculator right now? Just send me a picture of it.
Okay, yeah. I mean, if like knowing in my head, if I were to make this into scientific notation, I would know to put the exponent, but my calculator doesn't do that.
So is your calculator doing this? It's just giving you this big, giant, long number?
Yes.
Yeah, that's fine. You're going to have to convert it to scientific notation. I hear some of you have the fancy calculator where you could just hit the button and it converts it to scientific notation, right? Now that we're so far in this class, I'll tell you about the button. Some of you guys have the button. It's called the ENG button. It will just turn it into scientific notation for you. It's lovely. If you send me a picture of your calculator, I'll tell you where the button is. And I'm going to warn you, those of you with the gray and white green calculator, you don't have that button. Yeah, that one, Abby doesn't have that button.
So can I take a picture of the for this problem? Can I send you a picture of my calculator? Because I have the TI-84, so I would assume it would do it for me.
Yeah, that one has the button. Yeah, send me a picture of it.
Okay, thank you.
And if any of you want to just text me a picture of it, I might not get to you right now in lecture, but I'll send it to you right after lecture. I'll tell you where the buttons are. Okay, so let's try the water one. So everyone work on this water one, and this will be our last of the day. This is it. Maybe you need to upgrade your calculator. You guys are funny. Okay, I'm seeing a lot of them come through now. I'm going to give you another minute, and then I'm going to do some things. You're going to tell me what I've got wrong. The last problem of the day, I promise. $1.6 times 10 to the 9th. I'm seeing like 7 of those, yes. Okay. That's a shit. You guys are hilarious. Okay, so tell me what I've done wrong.
It's 2H2, whatever.
Right. This, again, really common mistake. This is H2, so don't forget this needs to be 2 H2s, right? Super common mistake, especially when we're going so quickly sometimes. Okay, units. And 2 moles of H2. This time we're going to water. 2 moles of water. I get the question sometimes, if they're both the same, do you have to write them? Yes. Yes, you do. Water is 18.02 of water. Okay. C times 2 times 18.02 divided by I'm seeing lots of these. I got 1.6 times 10 to the 9th grams of water. All right, so make sure you can get this in your calculator, that you get 1.6 times 10 to the 9th. So those of you who don't have it in scientific, this is what my calculator said. Okay. Any questions on this one? So this is 1.6. Everyone's got this as a number? Making sure you can get this in your calculator. Okay, so now let's look at our third and last question of the day. No more math that you have to do. The last question was, does the mass of the water vapor equal the mass of the reactants? Okay, so our reactants are H2 and O2. So for our H2, we have, 1.8 times 10 to the 8th grams, right? That's our H2. Our O2, what was our O2? Was it the 1.6 times 10 to the 9th? Yeah?
No, 1.4.
1.4 times 10 to the 9th?
Yeah.
Yeah.
For O2.
Yeah. That's our O2. And then our water, so do our reactants equal our products? And then our water was the 1.6 times 10 to the 9th. The question is, do these equal each other? Well, let's just see. 1.8 times 10 to the 8th plus 1.4. Oops, my calculator's not working. 1.8 times 10 to the 8th plus 1.4 times 10 to the 9th. Do they? Yeah, I got 1.58 times 10 to the 9th. And this is 1.6 times 10 to the 9th. Well, I mean, we'll just go back to this, our two sig figs. Look, they do equal each other, right? So the mass of our reactants equals the mass of our products. Who remembers what law that is? Anyone? Anyone?
Law of conservation of mass?
Yeah, this is the law of conservation of mass, right? We just did a lot of math, but we proved that it is true. So in rocket fuel, when they have 1.8 times 10 to the 8th grams of hydrogen, this is how much oxygen it takes to lift the rocket off. And then this is how much water is produced, right? So the mass of the reactants does indeed equal the mass of the products.